The hardest part of colonizing space isn't getting there, it's making sure the colonies still exist 100 years later. Because history suggests that founding a settlement is often easier than keeping it alive. The Aurora Effect. One of the ideas that sometimes appears when discussing interstellar colonization is called the Aurora Effect, named after Kim Stanley Robinson's novel Aurora. The core premise is fairly simple. Even if a civilization successfully sends a colony ship to another star system, there is no guarantee the settlement will succeed once it arrives. Getting there is only the first challenge. Staying there and building a thriving civilization may prove far harder. And while the reasoning and circumstances in the novel aren't terribly realistic, the core premise is certainly valid. As difficult as the journey might be, it's only half the job. Forging a new world is no easy task. Nor is it hard to imagine that people accustomed to far better lifestyles in a high-tech, post-scarcity future might hesitate to volunteer for such a mission, or change their minds later. A generation ship might travel for centuries across the interstellar void. The people who arrive may not even be the children of the original volunteers, but the grandchildren of their grandchildren, raised in an entirely artificial environment. When they finally reach their destination, they may find the planet they plan to terraform is hostile in unexpected ways. Spoiler alert, but in the story, native microbes make humans sick, which, as we discussed before, is unlikely, since we would probably be biochemically incompatible with alien life. However, some form of biochemical friction making things harder is reasonable, and more to the point, the real problem might simply be that transforming the world into a living ecosystem is far more difficult than anyone anticipated. In that situation, the colonists might decide the project simply isn't worth the struggle. They might turn the ship around, settle for a minimal outpost that never grows very large, or abandon the effort entirely. The Aurora Effect highlights that colonization is not just a technological challenge, but a biological, economic, and cultural one as well. Even if the engineering works perfectly, the human side of the equation may falter. More broadly, the concept emphasizes that good worlds may be rare, and even when we find them, establishing a self-sustained civilization on them is an immense undertaking. A small colony trying to survive on a hostile planet may remain fragile for centuries, vulnerable to disruptions that a mature civilization could easily endure. However, the Aurora Effect is less an argument that colonization is impossible than a reminder that early colonies are fragile systems. And fragility brings us to the next major challenge: ecology. Ecological fragility and the minimum viable ecosystem. When we think about sustaining life in space, we often imagine greenhouses, hydroponic farms, and maybe a few animals. But real ecosystems are vastly more complicated than that. Earth's biosphere did not appear overnight. It evolved over billions of years through countless feedback loops between organisms and their environment. Plants modify the atmosphere. Microbes alter soil chemistry. Animals distribute seed and nutrients. Entire ecosystems form networks of interdependence so complex that even today we are still discovering new connections. And while we could in theory bring many of those organisms along, we can't simply wallpaper Earth's ecosystems onto a planet with a different day length, different year, different tides, different soil chemistry, and expect those delicate systems to function in the same balance they do here. Much adaptation and careful tweaking would be required. A space colony attempting to replicate that system must essentially compress billions of years of ecological development into a carefully engineered life support system. This means identifying and maintaining what we call a minimum viable ecosystem, the smallest ecological network capable of supporting long-term human life. That ecosystem includes far more than crops and oxygen. It includes soil microbes that break down organic matter and recycle nutrients. It includes bacteria that fix nitrogen from the atmosphere so plants can grow. It includes pollinators that enable many plants to reproduce. Even the microbes living inside our own digestive systems are part of this network, because human health depends heavily on those microbial communities. Leave out one critical piece, and the consequences may take years or decades to appear, but when they do, it can cascade rapidly. Imagine an agricultural system that relies on pollination but fails to include the right insects. The first generation of crops might grow successfully, but over time, yields decline as pollination fails. Or imagine soil ecosystems that slowly degrade because essential microbes were never included in the colony's biosphere. In an isolated colony, such failures cannot easily be corrected by importing replacement organisms from the surrounding wilderness, the way they might be on Earth. The ecosystem itself is a machine, and if one part breaks, the whole system begins to degrade. Designing robust ecosystems, therefore, becomes one of the central engineering challenges of space colonization. A successful colony must treat its biosphere not as a passive environment, but as an actively managed system, carefully monitored and constantly maintained. Yet even if the ecology is perfectly designed, there remains another biological challenge: the long-term health of the population itself. Mutational load and genetic drift. Small populations face biological challenges that large populations rarely notice. One of these is genetic drift, the gradual accumulation of genetic changes simply due to chance in a small breeding population. In isolated environments, this can lead to what geneticists call mutational load, the slow accumulation of harmful mutations that natural selection cannot efficiently remove. In very small populations, this process can become self-reinforcing through a phenomenon known as Muller's ratchet, where deleterious mutations accumulate generation after generation without being eliminated. While Muller's ratchet is the most severe in asexual populations, it can still affect sexual populations when breeding pools become very small, because genetic drift can overpower natural selection. Radiation exposure may worsen this problem. Even with shielding, space environments often expose settlers to higher levels of radiation than Earth's surface. Over long periods, this increases mutation rates and adds additional stress to the genetic health of the population. Historically, isolated human communities have often avoided severe genetic degradation by maintaining relatively large populations or by exchanging people with the neighboring communities through trade or conflict. But an early space colony may not have that luxury. If the population is small and isolated, genetic problems may emerge slowly but steadily over generations. And we deep dived into that in our recent genetic bottlenecking episode. Fortunately, future technology offers several ways to mitigate these risks. Colonies may maintain vast libraries of stored genetic material from millions of individuals on Earth, allowing them to introduce new genetic diversity whenever necessary. Advanced medical technologies may detect and correct harmful mutations before they spread through the population. Genetic engineering itself may even allow colonists to repair or redesign genomes as needed. We need to be mindful, though, that this isn't just humans we're talking about. It's many thousands of species of large organisms and countless microscopic ones. Moreover, all of these solutions depend on maintaining sophisticated medical and technological infrastructure. Lose those, and you might collapse over time. The classic science fiction and fantasy series Dragon Riders of Pern by Anne McCaffrey illustrates both how powerful genetic engineering can be for a colony and how fragile a settlement becomes if its knowledge base collapses. In that story, the society's apparent medieval technology isn't a cultural choice. It's the long-term consequence of losing access to their scientific archives. And while not everyone thinks gaining their old knowledge back is good, overall they aggressively pursue lost knowledge throughout the main series, something we also see with the Martian Mechanicum of Warhammer 40,000. The Information Umbilical. Physical cargo is heavy. Information is almost weightless. But not everything can be sent as a blueprint. Earth colonies may still depend on shipments of rare elements, complex electronics, or specialized isotopes that their local industry cannot yet reproduce. You might profitably ship computer chips across even interstellar distances. A future colony in this solar system might be separated from Earth by millions or even billions of kilometers, but data can travel across those distances in minutes or hours at the speed of light. If a settlement possesses advanced fabrication systems, robotic manufacturing, and the raw materials needed for production, then a message from Earth may be enough to solve many problems. Indeed, even genetic material can be sent digitally and printed. While we are currently in the early stages of developing digital to biological converters, or DNA fax machines, this technology ensures that the colony can receive the blueprints for new vaccines or improved crop strains at the speed of light. Imagine a life support system failing in a distant colony. The settlers may not know how to repair it immediately, but they could transmit diagnostic data back to the engineers on Earth. Those engineers could analyze the problem, design replacement components, and send the blueprint back as digital instructions. The colony then fabricates the parts locally. In that sense, an interplanetary colony connected to the broader civilization by data networks is never truly alone. This doesn't help interstellar colonies as much, when those distances rise from millions and billions of kilometers to trillions and quadrillions. The real danger is not losing access to hardware, but losing access to knowledge. A corrupted database, a lost archive of engineering designs, or the gradual erosion of technical expertise could be far more dangerous than the loss of a single shipment of equipment. Messages home asking for help, even if they are received and acted on, may take centuries to get a reply, and even neighboring colonies might be a decade away. so maintaining this information umbilical becomes essential for long-term survival. Colonies must preserve vast libraries of technical knowledge, scientific research, and operational procedures. They must ensure that future generations understand not only how their systems work, but why they work. Because if your lifeline back home breaks down, rebuilding any knowledge from scratch in an isolated environment may take many generations. Incentive collapse. Finally, we arrive at perhaps the most unpredictable factor in any colony: human behavior. Travel 1 trillion miles to a strange new world, and it's still people that are the unpredictable quantity. Colonies do not fail only because machines break or ecosystems collapse. They also fail because cooperation breaks down. When resources are abundant and the future appears secure, societies tend to cooperate easily. But when resources become scarce, incentives begin to shift. History often shows people burning their ships upon arrival to symbolize that there was no going back, and to prevent anyone from organizing a return home. We tend to assume that option disappears automatically in space colonies, because the journey is so difficult to make in the first place. But in practice, that may not be true. People may decide they no longer want to be part of that mission, even those who once believed in it passionately. And the future may offer alternatives. We often assume people reach new colonies in stasis for the trip, and those systems continue to function after arrival. They might even serve another purpose. A colony can keep many colonists asleep and only wake them gradually to avoid placing too much pressure on early life support systems. But that same technology could also become an escape hatch. Someone might place themselves back into cryogenic storage and wait decades, perhaps even centuries, for a passing ship to detect a beacon and retrieve them. In that sense, people might still have the option of abandoning the colony, and they do so quietly rather than dramatically. Individuals may begin prioritizing personal survival over collective success. Groups may compete for control of critical resources such as food production, energy generation, or life support infrastructure. Leadership may lose legitimacy if the population believes decisions are being made unfairly. Rather than viewing these conflicts simply as personality disputes, it is often more useful to examine them through the lens of game theory. Every society depends on systems of incentives that encourage cooperation and discourage destructive behavior. In extreme environments like space colonies, those incentive systems must be especially robust. We often take it for granted today that delayed gratification is the key to success, and it seems reasonable to expect that people volunteering for decade-long journeys to distant worlds would possess plenty of patience, especially if life extension technology has been invented by then. But delayed gratification only works when people believe the future reward is real and worth waiting for. This is often not the case. Patience can sometimes be a mistake, but people also tend to see reasons for haste far more often than logic or circumstance justify. Especially in difficult circumstances, many may conclude that patience is not paying off, or worse, that it never will. A well-designed colony must therefore ensure cooperation remains the rational choice even during hard times. Transparent governance, fair resource distribution, and strong institutional frameworks can help maintain stability when stress increases. Because in a fragile settlement surrounded by a vacuum, social conflict is not merely political turmoil. It can become an existential threat. The weight calculation. Another subtle danger facing young colonies is something we might call the weight calculation, sometimes known as the innovation trap. If the civilization back home is still advancing rapidly, settlers may suspect that a better expedition is always just around the corner. Faster ships, better automation, improved terraforming tools, superior seeds and microbes, or simply more people and equipment. Why spend decades wrestling a stubborn Martian crater into farmland if a new mission might arrive in 50 years with vastly superior technology? Why invest enormous effort building heavy industry if automated factories from Earth might soon reach the system and make those efforts unnecessary? This temptation to wait can quietly stall development. In fact, we've arguably seen something like this on Earth already. Since Apollo, there's often been a tendency to delay permanent lunar infrastructure while waiting for the next generation of technology that might make it safer, cheaper, or easier. And speaking from my experience as the president of the National Space Society, I've heard that argument many times. Space engineers and advocates alike point to it as one of the habits that slowed progress toward the stars. The idea that we should wait just a little longer for the next breakthrough before committing to building anything permanent. Science fiction often plays with the same idea. A slow generation ship drifts toward a distant star for centuries, only to be overtaken by a faster vessel launched later after a better propulsion was invented. Viewers then ask why the original crew didn't simply wait for superior technology. Of course, they assume such breakthroughs are inevitable, which they rarely are. And this is not just a space exploration problem. Large infrastructure projects on Earth sometimes stall when investors believe a new technology will soon replace the current one. Electrical grids, transportation systems, and industrial upgrades can all be delayed by the expectation that something better is just around the corner. And it often is. But on a frontier colony, hesitation can be dangerous. A settlement that delays building redundancy and self-sufficiency may never reach the stability it needs to survive. In other words, progress elsewhere can paradoxically weaken a colony if it convinces settlers their own work is a temporary or obsolete one. Successful colonies therefore need incentive structures that reward building the long-term resilience even if reinforcements eventually arrive. Otherwise, the pioneers may stop acting like founders of a civilization and start acting like caretakers waiting for someone else to take over. Engineering stable colonies. So, those are some of the many ways a new settlement can fail, and the next question is, how do you build one that does not? A few years back, we deep-dived pancosmorial theory, which gives us a useful way to think about this. At the fragile end are frontier outposts like early Mars bases, Titan mining stations, or simple generation ships, places that can survive for a time, but where one broken system can threaten everyone. More robust are the mature settlements, large rotating habitats, industrial asteroid clusters, and fully developed Martian cities that can operate for long periods without direct support. And at the far end are truly self-sustaining biospheres, whether on terraformed worlds or inside enormous orbital habitats, where collapse becomes much less likely because the ecology, economy, and industry all have redundancy built into them by sheer scale. And that redundancy is the real key. The first rule of a lasting colony is that bigger is safer. That's practically one of our channel mottos. If brute force isn't working, you're not using enough of it. A settlement of 10,000 may survive, but it will always be fragile. A settlement of 100,000 has more expertise, more trades, more spare hands, and more room for error. A settlement of 1 million begins to look like a genuinely sustainable civilization. Large populations stabilize genetics, diversify the economy, and make it much harder for the loss of any one specialist, greenhouse, or factory to become fatal. Needless to say, on the genetic side, it's not just the human population that matters if a colony is going to have more than a shallow and vulnerable ecosystem. That does not mean every successful colony must start huge. It means successful colonies need a path out of smallness. They must be designed to grow quickly past the fragile phase, or to compensate for it with heavy automation, stockpiles, and multiple layers of backup. A tiny outpost can survive, but only if it remembers that being tiny is a temporary condition, not a permanent business model. The second rule is that everything vital needs backups. Power, life support, food production, water recycling, communications, machine shops, all of it. A colony designed around single points of failure is not a dream come true for pioneering families. It's more like a hostage situation. If one reactor scram means everyone freezes, or one food system crash means famine, then the settlement is not robust enough yet. Redundancy is not waste in space, it is survival. And redundancy does not mean spare parts on shelves. It also means alternate ways of doing the same job, multiple power systems, multiple ways to grow or synthesize food, and several approaches to recycling air and water. Some failure is inevitable. A resilient settlement is not one where nothing ever goes wrong. It is one where something goes wrong and nobody dies. The third rule is industrial self-sufficiency. A colony is not truly secure until it can make its own replacement parts. That means metallurgy, machining, chemistry, electronics, and biotech. You do not need full independence on day one, but you need a path toward it. The moment a settlement can build its own infrastructure, it stops being just an outpost and becomes a civilization. That applies to ecology as well. Future colonies will likely carry huge biological archives, seed vaults, DNA libraries, microbial cultures, frozen embryos, and digital genomic records. If a crop fails or a pollinator population crashes, the colony needs a biological backup system just as much as it needs spare valves and reactor parts. You are not just carrying people into space, you're carrying a living toolkit for building ecosystems whenever they drift, degrade, or break. Automation helps enormously here too. Robots reduce the minimum population needed to survive. Instead of requiring thousands of highly trained technicians to keep every system functioning, machines can perform routine maintenance, inspect holes, repair damage, and run much of the heavy industry. Indeed, they may be able to do everything the colonists need to do, but at that point, they are no longer just machines, they are people who happen to be made out of iron, and thus colonists themselves who now also need machines to do their work for them. But in that sense, automation is not just labor saving, it's a force multiplier that lowers the fragility of small settlements and helps bridge the gap until they become large ones. And automation has another advantage. It reduces how much your colony has to consist of irreplaceable human specialists. If a robot welder breaks, you fix or replace it. If your only expert in pressure seal fabrication dies in an accident, the problem is harder. A colony that can embody skill in machines, software, and archives is less vulnerable to the loss of any one person. That does not make people less important, it makes them less likely to be single points of failure. Redundancy also has to exist at the mission level, not just inside the habitat. Never send one colony ship if you can send 3. Never place the whole future on a new world in one pressure hull, one landing site, one command team, or even one planet. There will likely be several good settlement candidates in a given star system, even if none are ideal for classic terraforming. Distributed colonization across the system, several habitats, multiple settlements, separate depots, makes a civilization much harder to wipe out in one accident, one epidemic, or one bad political decision. This is one place where science fiction often cheats a bit. We love the image of one brave ship arriving in a new world to found a whole civilization. I think it's a great story, but it's also a terrible plan. Real colonization will likely look messier and more redundant. Convoys, follow-on missions, orbital infrastructure, backup sites, cargo depots, and spare habitats. More like building an industrial region than planting a flag. And that is really the deeper point. Colonies avoid early collapse when they stop being outposts and start being systems. Not one dome, but several. Not one crop, but many. Not one reactor, but a grid. Not one expert, but a profession. Not one settlement, but a network. The goal ultimately is not to build a perfect colony, it's to build one that can take damage, lose people, survive mistakes, and still keep going. Because a settlement does not prove it is viable when everything works exactly as planned. It proves it when things go wrong, and it endures anyway. We talk about building new settlements in space and overcoming technical and logistical challenges, or how settlers will behave. But once people live there, someone has to decide how the settlement is run. And, done poorly, it can ruin even those high-tech space colony. What happens when the person in charge begins treating the colony like a personal kingdom? History, fortunately, or unfortunately, provides an extensive catalog of what not to do. That makes Mad Kings from real-life lore such a fitting series to watch on Nebula. It explores some of the modern era's most bizarre and terrifying rulers, dictators, and would-be monarchs. People who gained enormous power and then used it for vanity, brutality, strange personal crusades, and decisions that would seem excessive even from a poorly written fictional villain. You can watch the complete 6-part Mad King series on Nebula, along with my full SFIA catalog, monthly exclusives, bonus episodes, and regular episodes early and ad-free. My link or the QR code gets you 50% off an annual plan, or 40% off lifetime access, while directly supporting SFIA and the other creators making these shows. From fragile outposts to stable civilizations. But survival is not just an engineering problem. Colonies must also survive economically. A settlement that produces nothing of value will struggle to justify continued investment from wider civilization. Advanced societies might view colonization as worthwhile in its own right, and be willing to subsidize it generously for a time, but the costs involved are astronomical, and even generous patrons eventually run out of patience. Space opera often imagines colony worlds rebelling against a homeworld that retaliates with an embargo on air or water, or even open warfare. As we discussed in our Rebel Colonies episode, neither of those resources would realistically be in short supply, and the military situation is far more complicated than what science fiction suggests. But in a pan-cosmorial context, a homeworld might not need to blockade life support or send in space marines. It only needs to threaten the thing a young colony cannot yet produce on its own. And that might include genetic samples, complex microchips, specialized software, technical schematics, or even cultural products like entertainment and media that help keep our distant society connected to the wider civilization. Fortunately, space offers many potential exports. Asteroids may contain rare elements and industrial metals. Ice-rich worlds can export propellant. Microgravity manufacturing may produce unique materials, pharmaceuticals, or delicate structures that are difficult to produce in a gravity well. Colonies may also produce scientific discoveries, data, and perhaps most importantly, energy. Trade networks bind colonies together into a larger civilization. A connected colony benefits from markets, migration, and technological exchange. An isolated colony must reinvent everything alone, and trade does more than move cargo. It moves ideas, people, spare expertise, genetic diversity, political attention, and the simple but critical fact that other places have a reason to care whether you survive. In that sense, the safest colony is not necessarily one with the thickest hull, it's the one with the most relationships. And that brings us to one of the more surprising insights about space colonization. Planets may not always be the best places to settle. A planet has obvious advantages: gravity, atmosphere, and enormous natural resources, but also imposes what we might call a gravity well tax. Every kilogram you move up or down that well costs energy. Transport becomes expensive. Escape becomes difficult. If a colony on a planet starts failing, leaving it may be harder than surviving it. Orbital habitats have the opposite problem. They avoid deep gravity wells and can be built exactly to human needs, but they impose a maintenance tax instead. Hulls need repair. Radiation shielding must be maintained. Rotation systems, station keeping, and structural integrity all require constant attention. Still, those costs are predictable and controllable. A habitat can be built for Earth normal gravity, an ideal day-night cycle, and a carefully managed climate. A planet has to be adapted to, often at an enormous cost. So by the time humanity begins serious interstellar colonization, it is entirely possible that most people already live in artificial habitats. If that is the case, moving to another star system may not require landing on a planet at all. You simply bring your habitat with you. A rotating cylinder orbiting the Sun is already halfway to being an interstellar vessel. That changes the whole colonization equation. You no longer need to search for the perfect Earth clone. You just need matter, energy, and enough stability to build with. A star system full of asteroids, moons, and sunlight may be more attractive than an Earth-like planet with a difficult biosphere and a deep gravity well. So one of the best ways to avoid early collapse may be to stop assuming colonies must begin on planets at all. Multiple expeditions dramatically increase the odds of success. If one fails, others may survive. If one settlement chooses a bad site, others may pick better ones. If one leadership team proves incompetent or unlucky, others may not. Colonization should also be distributed across a system rather than concentrated in one location. Several habitats, mining sites, and settlements spread across moons and asteroids make the population far harder to wipe out through a single accident, war, or disaster. A civilization spread across a system can lose one node and keep going. One concentrated in a single dome or valley may not. However, even when colonies fail, their infrastructure rarely disappears entirely. A derelict O'Neill cylinder is not worthless. It's a gigantic structure full of metal, shielding, machinery, and habitable value. Future settlers can reclaim it, assuming it didn't crash into the planet it was orbiting. Failed settlements in space or groundside may become salvage yards, industrial sites, emergency shelters, or the foundations for entirely new communities. Failure does not necessarily destroy the frontier. It often leaves resources behind for the next generation of explorers. That, ultimately, is the broader lesson here. The early centuries of space colonization will probably be messy. Some settlements will struggle but scrape by. Some will collapse and perhaps recover. Others may be abandoned entirely. Many will need reinforcement resources and settlers from home. But each attempt teaches future settlers how to build better systems. Humanity learned how to cross oceans through failed expeditions. We learned how to build cities through collapse, famine, war, and rebuilding. And we will likely learn how to settle space the same way. The first colonies may be fragile, but fragile does not mean doomed, because each generation will inherit the lessons, infrastructure, and knowledge left by the last. Settlements grow, networks form, trade routes appear, industry spreads outward, and eventually the frontier stops being a scattering of precarious outposts and becomes a civilization. So those first colonies may indeed be fragile, but eventually those colonies grow into cities. Cities grow into civilizations, and once that happens, the frontier stops being a hostile wilderness, and it becomes home.